Hi, welcome to Lesson 8 in Unit 3 in our course on AP Calculus. Unit 3 is all about differentiation rules. And now it's time for us to learn about the exponential function. This is one of the most fascinating and intriguing results of our calculus, so I'm really excited to share it with you. Let's begin with a function 1 plus 1 over x to the x. I want you to use your calculator to evaluate this function for values of x that are approaching infinity. And then, according to your tables, I want you to predict the limit as x goes to infinity of f of x. Well, I'd like you to do this first on your own, but pause the video and do it, and then I'll go through it with you on the Desmos. All right, so I'm just going to pull up the Desmos graphing calculator, and I'm going to go ahead and type in, we're looking at 1 plus 1 over x to the n. One plus 1 over x to the x, I should say. All right, let's take a look at a table of values now. So I'll just, to make a table of values, I can just say f of x equals. Then down here, I can say f of x again. And go to the settings and click on table. There we go. All right, so I'm going to look at this for some really big values. So let's start talking about like 10. Ooh, big value, right? Well, it turns out that this particular function converges really quickly. 20, 30, let's bump it up to 100, 200, 300, 400. We're not even that far out, but we're getting really close to a number, aren't we? You could see that, well, at some point, y'all, at some point you're going to have some underflow errors, so I probably shouldn't go much further than that. Yeah, I'll try it. All right. Okay, let's try this. 3,000. Okay. Let's do 10,000. 2.718141459. Let's try 2,000. 2.7182139. Let's see if it can take it even further. Let's do 200,000. 2.718275. All right. 1 million. 2.7182805. Okay. What? 10 million. 2.7182817. Do you recognize this number? I'm not going to fill that in. I've already made the table here on the Desmos, so you can fill that in if you want. But do you recognize that number? 2.718281828. That number is E. This number is approaching E, and that gives us our calculus definition of E. The definition of E is the real number value that is the limit as n goes to infinity of 1 plus 1 over n to the n. So the definition of, if that's the number, well, then what is e to the x? Simply replace 1 with x. So, for example, let's go back and let's compare e to the x now. I'm going to do e to the, well, let's do 0.1253. 0.1253. And I'm going to go over here and I'm going to put in e to the, what did I say, 0.1253. And it should converge to roughly the same number. Now, these things here, I don't need them. I don't know why they're there. 1.1333. All right, let's try another one. Let's do e to the, let's try 8.945. 7,669. 8.9. What did I say? 8.9. I got to check again. 45. And you'll notice it's converging again to that same value. So by just replacing the 1 with an e, with an x, we get e to the x. Like with so many things in calculus, we have an alternate definition that is useful in some situations. If we let m be 1 over n, we can show that this e to the x limit is the same as 1 plus m to the 1 over m. So I've got 1 plus 1 over x to the 1 over x. And I'll just, again, make a table of values. But this time we're going to be going towards 0. So let me clear out all this first. So I'll start with a 1. And then do 0.5, 0.3, 0.1, 0.2, 0.01, 0.001, 0.001, and it's the same kind of thing. But now it's a limit as the value is going to 0 is also approaching it. So that's the alternate definition there, that we can express e as the limit as m goes to 0 of 1 plus m to the 1 over m. All right, so practice 8.1. I want you to use a calculator to evaluate and round to 3 decimals. Basically, I just want to make sure you know where this button is and what to expect. All right, so for e to the third, you should have 20.086. For, let's see here, e to the negative 1, 0.368. And finally, e to the 0, well, you shouldn't need a calculator for that, right? That should be just 1. All right, I want you to sketch the graph of e to the x. It's a graph family of functions you should know from algebra. Graph it the best you can and evaluate these two limits here. All right, let's go over it. So a sketch of e to the x, e to the x looks like this. It's got a horizontal asymptote at y equals 0. It goes through 1 on the y-axis and then shoots up very quickly. So we know that the limit as x approaches infinity is going to continue rising towards infinity, but the limit as x goes to negative infinity, that is 0. You can just do direct substitution. E to the negative infinity becomes 1 over e to the infinity. E to the infinity is an infinitely huge number. 1 divided by an infinitely huge number is going to 0. All right, sketch the following. Yeah, let's do some basic transformations just while we're thinking about it. Pause the video and give that a chance, to give yourself a chance to do that. We got just a few of them, and then we'll go over them. All right, let's go over A. So we know the shape of e to the x starts small and then rises up. When you put a negative on the x, it's just going to flip it over the y-axis. So instead now it's going to look something like this. And if you haven't already, do B, e to the x plus 3. All right, well, that's just going to shift it up 3 units, right? So 1, 2, 3, and so now this is this horizontal asymptote there. So it starts very flat and then accelerates upwards. And then this one here, e to the x plus 3 is going to move it to the left 3. So we're used to it going through 0, 1. Now it's going to go through negative 3, 1. So it'll, again, start very close to the x-axis and then shoot up very quickly. All right, so now let's talk about the derivative of e to the x. The derivative of e to the x is e to the x. That's right. The derivative at any value x is the y value. In other words, the slope of the tangent line at any x value is the same as the function's value there. Quite remarkable. The derivative of e to the x is e to the x. For a proof of this derivative rule, please check the end of these notes. We can go over at the end of the video. It is a little bit, it's tricky. The proof is tricky. There are other ways to come about it depending on the direction that you learn calculus. But with what we have right now, we can prove this, but it is a bit tricky. So let's go on to the chain rule version. We know there should be a chain rule version. The derivative of e to the u is e to the u times du dx. Or in other words, the derivative of e to the u is e to the u prime. Let's find the derivative of each one of these. Okay, the derivative of y equals 5x e to the 5x squared. Well, the derivative of e to the u is e to the u prime. So, oops, I just wrote e, dy dx. So again, e to the u. So just write down what you see times u prime, which is 10x, the derivative of 5x squared. All right, let's do this next one. F prime of x is equal to, remember that 2 is really out here, y'all. So this is 2 cosine e to the x to the first power times, now I got to do the derivative of the inside, which is negative sine e to the x. Now I got to multiply by the derivative of the inside of the sine, which was e to the x. So we had the power rule, then we had to do the cosine rule, then we had to do e to the x. All right, pause the video and please do these practice problems. And I think that's all of them. Maybe I can get to where we can see them all. All right, well, just pause them and do them. All right, so on this one, y prime, the derivative of sine u is cosine u. Keep u the same. Times u prime. The derivative of 4 plus e to the 2x, derivative of 4 is 0. The derivative of e to the 2x is e to the 2x times the derivative of 2x is 2. E to the 2x times 2. All right, we got y equals e to the x cubed, so y prime is equal to e to the u times u prime. All right, we'll do the next one. If you haven't already, please continue to do letter C. All right, let's try this one. F prime of x. The derivative of cosine u is negative sine u prime. So for u prime, I'm going to have to use the quotient rule. So it's low, d high. The derivative of 2 is 0. Derivative of e to the x is e to the x. Minus high. D low, the derivative of 2 minus e to the x is negative e to the x. All over low, low. And that's it. Okay, I'm going to go ahead and move this out of the way. So pause the video if you're still writing that down. And give myself some room to do this next one. Secant e to the x. The derivative of secant u is secant u tangent u prime. So it's secant u tangent u prime. And the derivative of e to the x is e to the x. All right, we actually have x squared e to the negative 2x. That's going to require our product rule. So y prime is equal to derivative of the first times the second plus the first times derivative of the second, which is e to the u times u prime. Okay, so that's the end of that. Let's go ahead and call this a video. If you're interested in the proof of the derivative of the x, so I'm going to go through that at this time. If you're not, then I'll just see you in the next lesson. All right, so let me get some setups here. We're going to prove that the derivative with respect to x of e to the x is indeed e to the x. So we'll start with we'll use the original, the classic definition of derivative, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so what I'm going to do is I'm going to rewrite this using my properties of exponents. So e to the x plus h, I'm going to call e to the x times e to the h, because when you have the same base, you add them. So if I was adding, I could say it was like that. That actually gives me an ability to factor something out. So I have the limit as h goes to 0 of e to the x times e to the h minus 1 over h. So I'm going to pull out this e to the x out in front because it doesn't have an h in it. So as far as this limit goes, I know x isn't constant, but as far as the limit goes, as far as h is concerned, it is a constant. So I have e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Now, if you believe me that this limit is equal to 1, then I'm done with the proof, right? That the limit of e to the h minus 1 over h is 1 as h goes to 0. Unfortunately, and that's a little bit of work to prove that, but that's going to be really what this proof hangs on, is that this evaluates to 1. We could certainly, graph it, plug in the Desmos, use a table of values to convince ourselves that it's true, but we're going to try and show it analytically. Please note that at this time, this is an indeterminate form. If I plug in 0 for h, I get 0 over 0. Remember, e to the 0 is a 1. So let's take this limit and really focus on it. We're going to focus on right here. Okay, so the first thing I want to do is I'm going to do something kind of clever, which is my way of saying that I probably would have never thought of this, but somebody very good at math once did, and I respect it. So I'm going to let y equal e to the h minus 1. Simple variable exchange. This is totally reasonable to do as long as we go back later and fix it. And if I do that, if I say that, I can do some algebra and say that y plus 1 is equal to e to the h. And that's going to help me for reasons that will be shown. Actually, I think I'm going to write that a little differently. Just for purposes of beauty, I'm going to write it as 1 plus y is equal to e to the h. I keep looking over here at my notes because this is not easy. I want to make sure I get it 100% right. Now, the next thing I'm going to do is I'm actually going to take the natural log of both sides of this. And we haven't studied the natural log very much yet in this class, but you studied it in algebra before. And we will be looking at natural log very soon, so don't worry about that. But I am going to take the natural log of both sides. And that allows me to use some properties here. We know that the natural log of e, they are inverses of each other. So the natural log of e to the h cancels them out, leaving me just h. So what I now know is h is equal to the natural log of 1 plus y. Okay, so what all does that do? Well, let me show you. Let's go back and let's rewrite the limit. We're trying to figure out this guy right here. And we've done all this work, so how does this help us? Okay, so I'm going to rewrite this as the limit as h goes to 0 of y. Remember, e to the h minus 1 we said was y. Over, now h we said was the natural log of 1 plus y. Now I'm going to do something else. I'm going to write this y as 1 over y times the natural log of 1 plus y. All right. And again, the reasons why I'm doing this will be evident soon. But that's a true statement, right? I mean, this is y to the first on top, so I could write it as y to the negative 1 on bottom. But I just want to write it as 1 over y. And the reason why I'm doing that is so that I can use this logarithm property that says, if I have, 3 times the natural log of x, you learned in algebra that is x cubed, okay? Don't know if you can see that. Let me move that somewhere else. So remember this property, if you have like a constant, that's not x cubed, I'm sorry. I'm glad I rewrote that. I would have lost sleep over that. If I have 3 natural log of x, that's the same as the natural log of x cubed, because log expansion rules say I can take that power and bring it down in front, and I could also do the reverse. So that's exactly what I'm going to do. I'm going to rewrite this as the limit as h goes to 0 of 1 over the natural log of 1 plus y to the 1 over y. Okay. Now, I'm going to use my limit rules here, and I'm going to evaluate, and I can split up a limit of a quotient. The limit is h goes to 0 of 1. That's just 1. And then I have my composition of function rules. So I can go inside this limit and say that this is the natural log of the limit as h goes to 0 of 1 plus y to the 1 over y. So we're going to do it like that. Now, let's think about what does this mean that e to the h, that h is going to 0? Well, remember that y is e to the h minus 1. So if h is going to 0, then what is y going to? Well, as h goes to 0, since y is e to the h minus 1, we know that y is going to 0. So really, this is saying the limit as y goes to 0 of 1 plus y to the 1 over y. But do you remember what that is? Do you remember that rule? Let's scroll back up to our lesson and let's go back and remember that we know, if I can find it, the alternate definition is right here. That's what I have. I have that statement. So what is that? That must be E. That has got to be E. So this is actually 1 over the natural log of E. But what is the natural log of E? Well, it is equal to 1. The natural log of E is 1 because they are inverses, or, natural log is log base E. It's asking E to what power is E? E to the first is E. And 1 over 1 is 1. That's what we were trying to show, because we know that the derivative is e to the x times that limit. So we know the derivative is e to the x times 1, which is e to the x. And that's it. All right. I'll see you in the next lesson.